My name is Dave Tanigawa, and I'm a senior storage engineer with NetApp IT. According to a recent survey by the Armed Forces Communications and Electronics Association, data security and data loss top the list of data storage concerns for many organizations today. Whether we use SnapMirror, SnapCenter, FlexClone, SVM disaster recovery, SnapLock, or some other data replication or archive solution, the foundation for all of these is ONTAP Snapshot technology, and that is the focus of our discussion today. At a high level, ONTAP Snapshot technology gives IT administrators the ability to create space-efficient, point-in-time copies of key data sets in less than a second with no performance impact. Our team primarily manages snapshots at the volume level, but snapshots can also be taken at the aggregate or LUN level. We can also restore from snapshots at any level of granularity, single files, LUNs, or entire volumes. As organizations consider data recovery capabilities, key considerations include the recovery point objective, or RPO, and the recovery time objective, or RTO. The recovery point objective is the amount of data that can be lost without causing significant damage to the business, while the recovery time objective is the amount of time that the data can be unavailable without causing significant damage to the business, including the time spent recovering the application and its data. Compared to traditional data protection technologies, ONTAP snapshot restores can be done rapidly, providing an exceptional recovery time objective. Furthermore, the ability to capture frequent snapshots and retain over 2 million snapshots on a single controller enhance organizations' ability to meet tight recovery point objectives. ONTAP's Write Anywhere file layout uses metadata to point to data blocks on the disk, but it does not overwrite existing blocks. Updated data is written to a new block, and the metadata is updated. ONTAP snapshots reference metadata when creating a snapshot copy, rather than copying data blocks, eliminating the seek time that other technologies incur in locating and copying data blocks. This is what makes ONTAP snapshots particularly efficient. To understand the mechanics of how snapshots work, consider this illustration. For simplicity's sake, we'll assume we have a volume with one file, as shown on the left side of this illustration. Our file contains 3 data blocks, A, B, and C. All 3 of those blocks are written to disk, and metadata points to those blocks for our file. We create a snapshot of the volume, snapshot copy 1. Our snapshot now has pointers to blocks A, B, and C, but the snapshot consumes no space at this point in time because all of the blocks referenced by the snapshot are identical to blocks used by the file in the active file system. So the space is consumed only by the file in the active file system. We edit the file and note what waffle does. It doesn't delete or overwrite block B on disk. Instead, it writes to new block B1, and the metadata for the file is updated to reference B1 as part of the file instead of block B. Block B still lives on disk, but now it's uniquely associated with snapshot copy 1. With block B and block B1 both on disk, the additional space has to be accounted for somehow. So the space associated with block B is now attributed to snapshot copy 1. Since blocks A and C remain unchanged and part of the file at this time, the space for those blocks along with block B1 are now attributed to the size of the file and the active file system. If we take a snapshot of the volume now, snapshot copy 2 is going to point to blocks A, B1, and C. Since those blocks are still associated with the file in the active file system, snapshot copy 2 occupies no space. Deleting a snapshot only deletes the data that is uniquely held by that snapshot. So if I delete snapshot copy 2, I will free up no space. Snapshot copy 2 only points to blocks that are currently in use by the active file system, and it doesn't own any unique blocks at this point in time. However, if I delete snapshot copy 1, I also delete block B, which was uniquely held by that snapshot, and I free up the space that was occupied by that block. Deleting snapshot copy 1, however, does not delete blocks A or C because those are still active in the active file system and also referenced by snapshot copy 2. In a volume with a high rate of data change, data is being written to new blocks frequently, and the space occupied by snapshots will therefore grow more quickly as blocks are disassociated from files in the active file system. For our demo, I'm going to provide a quick overview of snapshot management capabilities in System Manager. I'll demonstrate a couple of snapshot recovery scenarios, and I'll point out a couple of CLI commands which are helpful for managing snapshots. I'm using an ONTAP 9.10.1 cluster, and I have a test volume here named DT snapshot test. I'm going to edit this volume so we can take a look at the snapshot settings for this volume. The first item here is snapshot reserve. So snapshot reserve ensures that there's space available in the volume for snapshots. This can be increased on volumes where there's a higher rate of data change, or it can be set to 0 if you don't want to use snapshot reserve. Snapshot reserve is configured as a percentage of the volume size. Snapshot reserve cannot be used by data in the active file system, but snapshots can consume space in the active file system if the space occupied by snapshots exceed the snapshot reserve. Scheduled snapshot copies are determined by the snapshot policy that's associated with the volume. And here we can change the policy that's associated with the volume if we want, but managing the specific details of the snapshot policy is done in a separate section under protection in System Manager, and I'll point that out in a minute. But here we can see the snapshot policy, all of the different schedules that are configured for this policy, the number of snapshot copies that are retained for each schedule, and any SnapMirror labels that are associated with each. SnapMirror labels can be important if you want to use the SnapMirror policy rules that pull snapshots with specific labels, and you want scheduled snapshots to be included in those transfers. The other options we have here at the volume level are whether we want to automatically delete older snapshot copies and whether we want the snapshot directory to be visible to clients. In other words, do we want users to be able to restore their own data? Okay, so here in the protection section, under Overview and Local Policy Settings, we have the snapshot policies. Now, these can be expanded to see the different schedules that are configured for each, along with any SnapMirror labels and the number of snapshot copies we're retaining with each of these schedules. We can edit any of these policies if we want to make changes to it. We can then, and here you can do anything you need to do to manage the policy. You can delete a schedule, you can add a schedule, you can change a schedule, you can change the number of snapshots for each schedule, you can change the SnapMirror label. Anything you need to do with the snapshot policy, you can manage here. In System Manager, we're looking at our test volume, DT snapshot test, and on the snapshot copies tab, I can see the snapshots that are currently on the volume. On my laptop, I've mapped to the share, and you can see that the volume is currently empty. So I'm going to create some test files and put some data in them. And take some manual snapshots. Okay, so from the command line, we can take a look at all of our snapshots, including the ones we just created manually. With the create time and snap mirror label arguments, we can also see when each snapshot was created and whether each one has a snap mirror label. The volume snapshot show delta command can be helpful to understand the difference in size and blocks between two different snapshots. If we specify one snapshot instead of two, it'll show us the delta between that snapshot and the active file system. And then the vol snapshot compute reclaimable command will show us how much space can be reclaimed if we were to delete a list of snapshots that we specify. Okay, so let's look at a couple of recovery scenarios. In our first scenario, I'm going to delete all of these files that we just created. Files are gone, and recovery from System Manager is ideal for a full volume recovery. So we're going to take our last snapshot, and we're going to recover from this one. Snapshot copy was restored. Refresh. Here's all of our files with all of our data intact. Next, what we're going to do is we're going to delete a single file. Let's delete test file 1. And one way to recover a single file is from the command line. Now here we're specifying the vserver, the volume, the path to the file we want to recover, and the snapshot we want to recover from. Test file 1 is back with all of its contents. Now let's say that someone came in and edited test file 3, and they added some new data. There are times when you don't necessarily want to overwrite the file in restoring it. So maybe you want to recover the original file to a new location so the user can compare the files and decide what data they want to save. So we're going to create a new folder here. And what we can do is, under properties, we can look at previous versions, find our most recent snapshot, open that, grab a copy of test file 3, and copy it to our restore directory. Now this test file 3 has the original contents, the original data, and the test file in the original location has the edited contents. And then we can leave it to the user to decide what data they want to keep, what they want to purge. So finally, let's look at a scenario where we want to restore to a point in time. Let's say we want to restore back to before we started working with all this test data. So let's find our snapshot that was created before all the test data was there. So that would be this hourly snapshot here. Let's recover back to that point in time. And when you recover from a snapshot, you'll see you get a message that says that all changes made after the snapshot copy was created will be lost. So we would expect these test file snapshots to be lost, but we will recover the volume to this point in time before that data was created. So we'll acknowledge the warning, restore. Test file snapshots are gone, and our volume is recovered to the point and was before we started working with the test data. So that's a quick overview of ONTAP Snapshots. We hope that you have found this video to be helpful and informative. Thanks for joining us for this video today, and we look forward to seeing you again next time.